Good morning, students. Today we'll discuss about the concept of eliminating ambiguity. In previous class, we have discussed ambiguity grammar. So it means when a grammar is having a two or more parse trees, at that time we will call it as a ambiguous grammar. So we need to remove the ambiguity from the grammar. That is the today concept. Okay, so you already know that ambiguity is nothing but suppose if for a particular person, if two names are there, so then from which name we need to call. So there is a confusion. Okay, so if you have only one name, so then obviously you can call that particular name. If a particular person is having two names, okay, so it's very difficult to identify with from which name we need to call. Okay, that is the confusion occurs in parse in compiler also. Okay, so here that is in a grammar, if we have more than for a particular string, so if we have more than two parse trees or a two left derivations or a two or more right derivations, so at that time we will call it as a ambiguity grammar. Okay, so we need to remove that ambiguity from the context free grammar. That is the concept of, okay, today's class. Okay, so here what do you mean by ambiguity? Okay, so today we will discuss the outline of this today's class is just removing the ambiguity grammar. What are the different ways of ambiguity grammar? How we will remove those ambiguity from the context free grammar. Okay, some grammars that are ambiguous can be converted into unambiguous. Okay, so some grammars they may have ambiguity, so we need to convert that one into unambiguous. So how can we convert? There are two ways, two methods we have to convert that unambiguous grammar, ambiguous grammar to unambiguous grammar. Okay, one is using precedence and associative of operators. Another one is disambiguity rule. Okay, so we have two methods to convert ambiguous grammar into unambiguous grammar. So one is precedence and associativity of operators, and third one is disambiguity rule. That is the second one. Okay, so here we already know the associative of precedence and associative of operators. Okay, suppose if you have arithmetic operators plus minus, division, multiplication, so all those things we will have. So minus, multiplication and division have highest priority than the plus and minus. Okay, so you're taking one example, we will discuss that how we will convert that ambiguous grammar to unambiguous grammars. So here convert the following ambiguous grammar into unambiguous. Okay, so here we have an, same thing, we are using same grammar. We have derived parse tree to left derivatives, right derivatives, and parse tree we will also derive all those things using the same examples we are taking, and we will remove that unambiguity from the grammar. Okay, so here they have given e tends to, that is e star e or e minus e, then e tends to e, that is square symbol. Okay, so e and e slash e. Okay, and e tends to e plus e, and e tends to e or id. Okay, so this is the grammar they have given. So using this, we need to convert that one to grammar to unambiguous, unambiguous grammar to unambiguous grammar to ambiguous grammar to unambiguous grammar. Okay, so here, so why we are called unambiguous, sorry, ambiguous, because using that we may derive the two different parse trees. Okay, so we may derive the two different parse trees, that's why we will call it as a unambiguous grammar. Okay, so I already discussed the derivation of two parse trees. Okay, so in previous class I have discussed that one. Okay, so here what are the different steps to convert ambiguous grammar to unambiguous grammar? So here the grammar can be converted into unambiguous grammar using the precedence of operators as well as associativity of operators as shown below. Okay, so here, so first we need to check the operators associativity and precedence. Okay, so here plus and minus, so they are left associative, yes or no? So plus and minus, they are left associative, and for that we are using non-terminal e. Okay, so our variable are a non-terminal e, and star and division, so that is also left associativity, and we are representing using t. And this square is having a right associative. Okay, so it will have the non-terminal used p. Okay, so here since there are three levels of precedence, okay, so we associate with three non-terminals. Why you are taking three non-terminals? Because we have three levels precedence. Okay, so here first we will give the highest precedence to the square, then after that star into division, and after that we will give plus and minus. Okay, so here, okay, so these things we need to, and associativity will be plus and minus will be left associative, star and division is also left associative, and the square symbol is also is the right associative. Okay, so here we have three levels of precedence, that's why we have using three terminals etp. Okay, and also an extra non-terminal f is using for symbol. Okay, generating the basic units in an arithmetic expression. Okay, so here when you are doing when you are converting ambiguous grammar to unambiguous grammar, so we will go from basic unit. Okay, so here basic unit is, that is we will derive that id is equal to id plus the string is id plus id into star id. Okay, so we need to, that is the base final thing is set of terminal strings. Okay, so that's why we are taking this basic unit as the first step. Okay, so we need to write the we need to write the production for the basic unit. Okay, so the basic unit in this expression are id, that is identifier, and parenthesis is expression. Okay, so parenthesis expression, that is this one. Okay, okay, so this one e within the parenthesis, no, that one that one will call it as a parenthesis expression. The production corresponding to this one we will call it as this, the last one. For extra non-terminal we are using that variable f. Okay, that is non-terminal f tends to e within the parenthesis, and this is the id. Okay, so this one you need to write when they are asking, because this is the basic unit. Okay, so then after that, after writing this, next step is which one is having highest priority. So here square symbol is having highest priority. Next highest priority is having a square, and it is right associative. So whenever it is right associative, okay, the production must start from non-terminal p. Okay, and it should have right recursive. So when it is right associative, in the production it should, right recursive should be there. So what is that right recursive? See here, so here p tends to f is nothing but for basic production. Okay, so f tends to erid. Okay, so that one square with p. So here p is there now, so p f square p. So it means, so here we can exchange this p value with multiple times, so at right side, that's why we are calling as a right recursive. Okay, suppose if p comes here and f comes here, that one will be left recursive. So because of this right recursion, okay, so because of this right recursion, we need to write the production such a way that this p will should come at right side. Okay, or it will be a p tends to f is nothing but a basic unit. Okay, so that is the next step, right assertive. And whichever, okay, after square, which one is having highest priority? Star and division. Okay, so next highest priority operators are star and division. Okay, so but they are left associative. Okay, so the production must start from the non-terminal t. Okay, so this for a star and slash we have used variable t. Okay, and it should be have left associative. Okay, so it means this t, the recursive should come at left side. Okay, so t star this p. Okay, so t star p or t slash p or p. Okay, so got the thing. So here the this one star and division will be represented using non-terminal t. Okay, and it is left associative. If it is left associative, the production must start from non-terminal t, and it should have left recursion. Okay, so it should have left recursion. It will be t tends to t star p or t tends to t slash p. and finally that last one will be a P. Okay, so like that we need to write the production for the star and slash. Okay, so next step is next highest priority, or after that we will have plus and minus. So for that they have, it is also a left associative. Okay, so it is also left associative. So the production must start from non-terminal E and it should have left recursion. Okay, so here E tends to E plus this T. Okay, or because E, why you are using E at left side? Because we need, this is left associative and it should write in a left recursion. Okay, so E minus T slash T. Okay, so E plus T or E minus T, or it will be T. Okay, so we have derived the production for plus and minus. Now the final grammar, which is unambiguous, can be written as, so it will be, so yeah, replace with E plus E, that one with this. E tends to E plus T. Okay, so R E minus T R T. So then T, the T will be T star P slash R T slash P R P, and P tends to F square P or F. This F tends to E or ID. Okay, so this is the an unambiguous grammar. From ambiguous grammar we have derived. So because of, I will explain once again. Okay, so because of this is the problem given, they have in exams, they also ask. Okay, so give this statement and convert this ambiguous grammar to unambiguous grammar. So they have given, so E tends to E star E or E minus E, E square E or E slash E, and E tends to E plus E. Okay, E tends to E or ID. Okay, so because here we are using this, we can, for the same string we can derive the more than one parse tree. So at that time they will specify the, it is ambiguous grammar. So it means you identify that it is an ambiguous grammar. Okay, so why ambiguous, I have discussed already in previous class. Okay, so now this class is to remove the ambiguity. Okay, so here, so because of this, so why ambiguity is there? So here there is no precedence. See here, so plus is here and star is there. This square is highest precedence. Okay, so but it is in middle. Okay, so this slash is highest precedence than E minus, it is here. So we need to write such a way that highest priority should come. Okay, so highest priority based on highest priority, that is precedence, and based on associativity. So we need to rewrite this grammar. Okay, so for that what we need to first identify the associativity and precedence. Okay, so here plus and minus, that is arrange the operators in increasing order for the precedence along with the associativity. So here operators along with the precedence, so plus and minus having a very less precedence, and star and division is more than second more precedence than plus and minus, and this square is having highest precedence. So and you also right identify the associativity. If it is left, plus and minus are left, star and division are left associated, and this will be right association. Okay, so for that, for each one we are using a non-terminals, ETP. You can use any terminals, that is not an issue. ETP we have used. Since all three terminals are precedence, and the last one we have now, so this E tends to ERID. So for that also we need one terminal, non-terminal, that one will be represented with F. Okay, so ETP, and the last one is F, generate the basic units of arithmetic expression. Okay, so from first we need to derive the production for the basic unit. Okay, so that is F tends to ERID. Okay, so this is the basic unit we have here. Next we will go for the, which one is the next highest priority. Now for that you need to derive the production. Okay, so your square symbol is having the highest precedence and it is right associative. When it is right associative, okay, so that right recursion should be there in that production. Okay, so here I will represent P tends to, okay, so here basic ID in previous we have taken F. Okay, so F square P, because why you are putting P here? Because of this right associative. Okay, F square P or F. Okay, so now we have created the production for square symbol. So next precedence you are having star and T, star and a division. So that is also left associative. That one will be used to representing using non-terminal T. So then see here, and this is left associative means it should be left recursion. Okay, it means that T should come at left. T tends to T star, and which one is the this precedence of production non-terminal is P, so that one you keep here, or T, same thing, division P, or it will be P. Okay, so like that, after that next precedence we will give to plus and minus, that is also left recursion. Okay, so left associative, that way we will take it as a left associative. So the production must start from non-terminal E, that you can take any terminal, non-terminal, no issues, and it should have left recursion. It means that E should come left side. Okay, so that is E tends to E plus this previous terminal is T, or E minus previous terminal T, or it will be T. Okay, so now you combine all those things from ascending to descending. Okay, so here E tends to E plus T or E minus T. So then T will be replaced with T star P, T slash P or P, and P will be replaced with F square P or F. F will be replaced with E or ID. So this is the final grammar, which is an unambiguous, and it can be written as shown below. Okay, so in exams they will give. Okay, so they can give any arithmetic expression. First thing is you need to identify the precedence and associative, that's all. Okay, so precedence, associatives you need to identify. Okay, and for each one you need to give the non-terminals and start from basic unit. Then after that, which one is symbols having highest priority, so they have given the productions, so you can replace that one with your new production. Okay, then after that next priority, like that. If you create this one, you will get a final grammar, and you will write from bottom to top. That's all, nothing is there. Okay, so this is using operators and associativity. I know precedence and associative, you can give, they can give any arithmetic expression, but the operators are same, precedence is also same, and associative is also same, so you can create for anything. Okay, so this is one way to remove the ambiguous from the grammar. Okay, this is one way to remove the ambiguous from the grammar. Next one is, okay, second one is, the concept is dangling else problem. Okay, so first this second rule is, that is disambiguity rule. So this to how we will disambiguity rule. So for that we will have the, first you need to understand the what do you mean by dangling else problem. Okay, so one problem is associative and precedence, another one is dangling else problem. What do you mean by dangling else problem? So if you understand this one, easily you can write the grammar for that. Okay, see here, in program we are using n number of nested if else statements. Okay, so n number of nested if else statement. See here we have taken an example, if condition 1. So inside that we will have condition, if condition 2, if it is true, execute statement 1, else executed statement 2. Okay, see here, suppose for example, if this condition is true, okay, if condition 1 is true, then we will come to here. If condition 2 is true, we will execute statement 1, else we will execute statement 2. Okay, fine. If the first condition is false, if condition is false, then what we'll do, we will come to else part and execute statement 2. Okay, if condition 1 is false, if condition is true, no issues. Okay, it will come to inner if condition, and it will execute, if condition is true, it will execute this one, or else it will execute statement 2. When the condition 1 is false, for the first if statement, when the condition is false, it won't execute these two statements, it will comes to here else, and it will execute the statement 2. But this is a wrong. Okay, so it won't execute that else statement. Okay, so that is the wrong. So we need to, this one we will call it as a dangling else problem. Okay, so this one we will call it as a dangling else problem, because wrongly the else is executed when the first if condition statement is false. Okay, so we need to overcome from this dangling problem. Okay, because when the if condition is true, no issues. When first if condition is false, so at that time by wrongly this else statement will be executed. Okay, so wrongly this else statement will be executed. So we need to overcome from this. How we will overcome? Simple. So this else is there now. So we need to combine this L whichever is nearer if statement. Okay. So here this L part is nearer to which statement? Which if? This is conditions, that is second if statement. It is nearer to second if statement. Then join with that second if statement. Then the ambiguity is removed. That's all. Okay. So that else, which the else is which nearer to which state, which if, then you can join with that. If it is nearer to second or first one, okay, you can join. If nearer to second one, you can join. But here, so usually this else will be nearer to, when it is if nested if, this else will be nearer to second if statement, then join with that second if, then it removes the dangling problem. So that one we are doing, that's all, nothing is there. Okay, if you understand this one easily, you will understand that next problem, same thing. Okay, so here this is this ambiguity rule. So we will have I will discuss using one problem. So we have already seen in the previous problem that grammar corresponding to if statement is ambiguous. Okay, so in previous class we have derived using this grammar we have derived okay, S10 to ICTS and ICTSESA. So we have removed for the same string we have derived the two, we have derived the two past trees and it is ambiguity. Okay, so this is due to an dangling else. Okay, that example I have given a dangling else. Okay, so we need to remove that dangling else problem can be eliminated, and thus ambiguity of the grammar is also eliminated. That dangling problem if we remove, then automatically ambiguity will be removed. How we will remove the dangling? The else, whichever is that else is nearer to which if statement, so you can join with that if statement, that ambiguity will be removed. Okay, so here what the, for example, this dangling problem will be explained with this. So here we have a s tends to this this the grammar we have given. So I stand for if keyword, c stand for condition. Okay, and t start for then, if then else. These three keywords we have in this if statement, if then else. Okay, so s stands for non-terminal. Okay, so that is starting, and e stands for else, and a and b are the statements. Okay, so this is the representation of these things. Since the above grammar is ambiguous, we get two different parts of the string, this string. Okay, it ib it bt btaea. Okay, so this one I will show you. So this thing, the same thing we have derived in previous class. Okay, so we will get the two parts tree. Okay, so here ICTS, so here s tends to ICTS. Okay, so here then after that s will be replaced with it, there's this it ICT SES, that is if condition is b and then if. Okay, so condition b and then condition a, else condition a. Okay, so this is the string what we are taking. Okay, so here this is the dangling problem is there. See here, if, okay, condition, then if. See here, if inside if condition b, then statement a, else statement a. Okay, so this is the a parse tree what we have, first parse tree. Okay, in leftmost derivative same thing. So for the same so we will use this this one we will use in second parse tree, ICTSES ICTSES, that is if. Okay, so state condition, then okay, then we'll have a statement. So in that statement, if condition is b, if condition, then condition a, else condition a. Okay, so this is the another parse tree. So for the same string we are getting two parse tree. Okay, since there are two different parse tree for the string itba, apply the leftmost derivation of the grammar, that is ambiguous we will get. Okay, when I combine this thing, we will get an ambiguous grammar. Okay, since there are two parse trees for the same string, the given grammar is ambiguous. Observe the following 2 points. In first parse tree, the tree is associate else with second if statement. Okay, in first parse tree, so in this parse tree, that is else part is associated with second if statement. In second parse tree, else is associated with first statement. Okay, see here. Okay, so this else is associated with first parse tree. Okay, so here, see here, this is e na, so this is associated with first parse tree. Okay, so then here e is associated with second if statement. This is the if statement, so this e is associated with if statement, this e is associated with first statement, and this e is associated with second statement. Okay, so this e is associated with second if statement, this e is associated with first statement. Okay, so here if this e is associated with second if, okay, and if e is associated with first statement, so then we will see what will happen. Okay, so the past is associated with else with second statement, and say else with the first statement. The ambiguity whether to associate else with first if statement or second if statement is dangling else problem. Okay, so whether to associate else with first statement or second if statement, that one we will call it so we don't know, so whether we need to associate with first or associate with second. So if you don't know that, that one we will call it as a dangling else problem. So then how can we solve this dangling else problem? Okay, so dangling else problem can be solved by constructing a unambiguous grammar. How we will construct unambiguous grammar? Come to here. Okay, so this is the production they have given, initial production s tends to ICSTS, that is this is C here, if condition then statement. So simple if statement, if condition then statement, simple if. So here if condition then statement 1 else statement 2, this is if else statement. Okay, then it will be s tends to a, okay, or C tends to b. Okay, so it means they have given if statement and if else statement. Okay, so when I derive these things, this if I add this s with this ICTS, then at that time we will have dangling else problem, or if I add this one with this else, yes, I will get a dangling else problem. Okay, in all programming language, when if statements are nested, first fast tree is preferred. Okay, so the general rule is match each else. Okay, so match each L with closest unmatched then. Okay, so here what you need to, you need to match that else whichever is nearer to, that is else is nothing but if then. Okay, so that is nearest to if statement, that's all. Match each else with closest unmatched if then. Okay, so this rule can be directly incorporated into this grammar, and ambiguity can be eliminated as shown below. Okay, so here this we will take care two things, matched statement and unmatched statement. Okay, so matched statement will be represented as M, unmatched statement represented by U. Okay, so here, so they have given ICTSES. Okay, the matched statement will be represent M if an if else statement, whether the statement yes before else or after else keyword is matched. So wherever that yes comes, so here when you are putting this, when you are replacing this yes with this ICTS, so at that time you will get a nested if else. Okay, so nested if else, then at that time we will get a concept of ambiguity, dangling else problem. So we need to remove that one. So here for that what we are doing, so we will replacing this yes with M. Okay, that is matched statement. Okay, so M stands to ICT, that is if condition true, then matched statement, else another matched statement. Okay, it means if normal if else, if condition is true, if condition is true, if condition is true, okay, if condition is true, then matched statement, else matched statement. Okay, so else matched statement or matched statement. Okay, so this is one thing. So then we no to put it in that nested. Okay, so next one is take unmatched statement represent using AU is one of the consisting of simple if statement. Okay, simple if statement you will take it as unmatched element. Okay, if simple if statement where the statement S is matched statement or unmatched statement, this equivalent production is whether it will be in simple if whether it will be matched or unmatched. See here, either it will be matched or unmatched statement. So here we will make it as one u tends to ICTS. If see here this one ICTS na. So if condition, okay, then statement. If condition, simple if statement. That's all. Okay. So this is simple if statement. So here this is if else statement. This is simple if statement. Another one is if statement, if else statement with matched and unmatched statement. If else statement matched unmatched element. If else statement whether the statement before else is matched and the statement after else is matched. Okay, so here if we are taking if else statement whether the statement before else is matched and the statement after else is unmatched, the equivalent production is that is u tends to if condition is true that it may be matched or it may be else unmatched. Okay, so if else statement with matched and unmatched statement. So here in if statement just if condition statement. Okay, so this one will represent as total unmatched statement. So here it means if you replace this u with ICTS. Okay, so here this is nothing but an if else statement where the statement before else is matched and the statement after else is unmatched. That one will be represent using u tends to I see if condition then match else unmatched. Okay, so match a statement or else unmatched statement. Let's see here. First thing is what we have done. So if else statement will be using we are replacing that yes with if else statement with matched statement. Okay, so here in this initial production we will have yes, so that one will be replaced with matched statement. If condition is true, matched statement, else matched statement. Okay, so this is if else. Then after that normal if statement. Okay, so normal if statement, that is if condition then yes is there. Okay, so that one we are making as a unmatched statement. S is matched, so here S is matched and unmatched, it may be a matched or unmatched element. So this one will make it as a u. So then this for if else statement we are putting matched or unmatched statement. That's all. That is u tends to I if condition then matched statement or unmatched statement. Okay, ICTMEU. Okay, matched statement or unmatched statement. This is if else statement with matched unmatched element statements, and first one is if else statement with matched statement. Okay, and this one will be unmatched statement for the same production. Okay, so then basic thing is the matched statement M and unmatched statement can be obtained using the statement yes. Yes tends to M or U. Okay, so S tends to M or U. So the final grammar, so from the basic S tends to M or U, and this matched statement ICT, that is if condition then matched statement or else matched statement, then u tends to if condition is if condition. Okay, so if condition then statement. Okay, if condition then statement, this is normal if statement. And here for unmatched if u tends to if condition then matched statement or unmatched statement. So it means we are segregating that one if else statement. Okay, so one if else statement, normal if else statement, that's all. Another one is we are combining. See here, I told that that else dangling else will be matched with nearer if statement. See here, so we have done this one here. So here I see that is if condition is true, then matched statements, else unmatched statement. Unmatched statements will be you can replace with ICTS. Okay. So here ICTS, that is if condition is true, matched statement, else unmatched statement. Inside you can use this if condition. If then, that's all. Okay. So here over the above grammar associates else with closest then and eliminate the ambiguity from the grammar. So here see here this in this else will be combined with if statement. So there is no ambiguity here. Okay, so there is no ambiguity here, and here we will else will be combined with this I only. So after that, if you replace with you with the ICTS also, if the if condition, then also we won't get any dangling else. Okay, so we won't get any dangling else. So like that we need to remove the unambiguity grammar with the ambiguity, remove the ambiguity grammar with the unambiguity grammar. So here what we are doing, so it means, so when you are given the productions, so you should identify the nested if. Okay, so nested if else. So when you are getting the dangling else, then that else part will be moved to nearer if statement. Okay, the else part will be moved to nearer to yeah, if statement, that is if and then statement. Okay, so for that what you have done, so we are taking that they have given the productions, so based on the first productions we are taking and we are writing simple if else statement. Okay, with the matched statements, matched statement, any statement you can write matched statement. So here if condition, then matched statement, cell matched statement. So here there is no dangling else we are getting. Okay, so then for this production you will make it as a one simple if statement. This is if condition then statement s. Okay, so here for that you are making one use one non-terminal u. Okay, so done. So then you can take on the if else statement with matched or unmatched statement. If condition, okay, if condition is true, then matched statement, else unmatched statement. So here in that you can replace with this ICTS. So at that time also we won't get dangling else. So in that we don't have any else statement at all. So it means this else is combined with this I only. That is in this, then the first then only we are getting. Okay, so like that. So for final thing you need S tends to final basic unit, that is S tends to M or U. Okay, so here from this grammar we won't get any ambiguity.